We are looking at the core component Holy Cross mock, and it's Holy Cross mock number 4. Question 4. The diagram shows some plant cells are seen through a microscope. We can tell they're plant cells because they've got cell walls in them, clear cell walls there. And you'll have looked down the microscope, you'll have probably looked at red onion epidermis, and see where it's grey here, you'll have seen kind of red blobs. Water relationships in the cell are related by the following equation. Nice simple equation, this thing equals that thing plus another thing. So water potential of the cell is the solute potential plus the pressure potential. And we'll discuss that again in a second. On the diagram labelled A plasmolysed cell, well, let's go for the most plasmolysed one, where the membrane has moved away from the cell wall and the cytoplasm has shrunk or reduced in volume. So we're going to have that there, A. We don't need to write plasmolysed cell, I think we can get away with A there. And B, a turgid cell, so one where we've got no plasmolysis occurring, so there's only one available there, so I'm going to go there with B. What proportion of the cells will be plasmolysed when their mean psi s equals the water potential? So where the solute potential equals the water potential of the external solution. It's going to be 50%. So if half look as though they're plasmolysed and half of them look as though they are turgid or look like they're turgid, so half of them look like A and half of them like B. So you need to count enough cells. So if you counted 100 cells and 50 were looking like A and 50 were looking like B, then that's the usual name. That is the next part, which is the famous incipient plasmolysis. Incipient plasmolysis, a crazy name. So half of them look plasmolysed, and that means that on average, although not true for many cells, on average the cell membrane is just resting against the cell wall and not actually pushing on it, and so the cell wall doesn't have to resist that force with an equal and opposite forces. So our pressure potential is going to be 0. A plant cell has a water potential of minus 600 and a solute potential of minus 900. Calculate the pressure potential. So this is just rearranging equations. So on here we want to make our pressure potential the subject of this equation. And so to get rid of this solute potential we need to minus it. So we're going to end up with pressure potential, and we're going to get rid of that, so it's going to be on its own, is the water potential of the cell minus the solute potential. So I've just rearranged that equation to make pressure potential the subject. Now we can just put in our numbers, so we can go just rewrite that here. Cell minus solute potential equals, and then we're given these numbers, so minus 600 minus, and this number is minus 950. And if you remember your school maths, if you minus a minus number, that's the equivalent of plussing it. Let's see if the trusty calculator agrees. So we're going to have 600 as a minus number minus 950 as a minus is 350. So plus 350, although we don't need to write plus. And what's the units? We should always put the units kilo Pascal, small k, big P for Pascal, and the small a. And that's our answer. So that actually means that in this situation the pressure potential has got a number, so the cell wall is having to resist the cytoplasm and the membrane pushing against it, and that's the force that it has to resist with an equal and opposite force. Draw an arrow to show the overall direction of water movement between the two cells below. Osmosis happens and water moves from higher to lower water potential. If I draw a little number line there, and if I put 0 there, and I put 300, 600, minus 300, minus 600, hopefully you'd agree that that's a number line that you met in primary school, but just with bigger numbers on. The highest numbers are over there and the lowest numbers are over there. Zero's in the middle, and so water will move from higher to lower in that direction. So from higher to lower. So drawing an arrow on, there it is. Calculate the water potential of the two cells at equilibrium. So water will move, and if we get more water in this one, well, the water potential will move up. That one's losing water, so it's got more solutes, less water, so that water potential is going to go into more minus numbers. So it's going to get lower. And they're going to meet in the middle. You can do this in your head. Halfway between 600 and 300, well, that's going to be 450. So the water potential of the two cells at equilibrium is minus 450 kilopascals. Or if you were calculating it, you go, what's the mean of these two? So minus 600, and you've got a minus 300. Divide that by 2. So add them up, divide them by 2, and that will give you minus 450. And that's 7 marks on water potential. Quite a difficult question if you haven't done some practice questions on that. But if you have done practice questions, then there's quite a lot that look very similar to that.